Good morning. My name is Jung Yo. I feel also comfortable with being called by last name Kwon because that's easier. I'm working with Konstantin Karamanis at UT Austin, and this work is collaborated with Wei Yudong and Damek at Cornell University. So as the title stated, our work is about answering one simple question: whether EM algorithm converges globally in the setting of two mixed linear regressions. And to simplify the discussion, we consider the setting where mixing weights are balanced and the problem is symmetrized, so the true parameter is either beta star or minus beta star. And we also consider this problem under standard statistical assumption, where X and noise are Gaussian. So EM algorithm is very powerful heuristic, it's very well known, and it works very well in practice, but it is also well known to be hard to analyze. And only recently, there's been made a progress since the work by Balakrishnan, Wainwright, and Yu. And the key idea of the work is connecting population EM to sample-based EM. And based on this work, many interesting convergence results have followed. And two recent papers even established a global convergence guarantee for two standard Gaussian mixture models. For mixture of linear regressions, there have been some attempts to prove the convergence guarantee. But however, these results were all end up in only giving the local convergence guarantee. And also they required the noise to be small enough compared to the signal strength. So it has been remained for a while whether EM converges globally or whether EM converges in low SNR regime. So one challenges or structural property of the two MLR is that the estimation error in L2 norm is not always decreasing, especially near the orthogonal region, this area. And within a few number of steps, and this result holds for both high and low SNR regimes, which also improves the previous local convergence results. And then we move on to finite sample EM, and for this, we will try to connect finite sample EM with population EM via concentration analysis. And since our argument was based on the convergence of the angle, especially cosine and sine, we need to give a concentration for cosine and sines too. And we again note that cosine theta is as small as 1 over root d during the initial phase. So the statistical error in cosine should be less than that. And it is true because the error in cosine is as small as 1 over root n. And it's because we are looking at the error in only one fixed direction, not in all directions in d-dimensional space. And n is usually larger than d over epsilon squared for d-dimensional regression problem. Therefore, we can get desired statistic concentration results for the cosine sequence. And the concentration in sine and L2 norm are relatively easy to verify with standard techniques. There is one hole to patch in our analysis, which is extra epsilon square error. We believe this is an artifact-bound analysis, but it could be a problem if epsilon is not too small compared to the dimension. So as to get around this technical issue, we suggested easy EM, which is just a slight variation of the finite sample EM for initialization. And there are several interesting things related to this, and I would be very happy to discuss it in offline. The sample complexity of the EM algorithm is optimal in D and epsilon, and especially in high SNR regime, EM is actually minimax optimal algorithm. And more importantly, we can guarantee an exact recovery as the noise power goes to 0. And this result is obtained via separate local analysis. For low SNR regime, it is still optimal in D and epsilon, but we think this result might not be tight in terms of the SNR. And we think it could be interesting future direction to explore whether EM is indeed input theoretically optimal algorithm or not. So in summary, we established the global convergence guarantee of the EM for balanced two mixture regressions, and the key idea is looking at the angle decreasing property. And we also showed that EM is minimax optimal algorithm in high SNR regime. And beyond this work, we established recently the local convergence results for MLR with more than 2 components, and global convergence results for a mixture of 2 components of log concave densities. And one challenge, I think, for the convergence analysis for the EM is considering the setting where x's for each linear component might have different and unknown covariances. And this is all I have for today, and thank you very much for the listening.